Hello folks! Well, this time around we're looking at higher order functions. So again, just any function that can take other functions as parameters. So we've seen this in Lisp, right? We've done this in Lisp, passing functions around as parameters, and there it was pretty straightforward. What we want to do today is take a look at it in C and C++. So the difference being, of course, that in Lisp you had a language where code is actually a perfectly valid data type. So it's perfectly natural to pass a function as data, and there are supporting functions to deal with that on the Lisp side from the callee's point of view. It gets a little bit more complicated in a statically typed language where you actually have to be able to try and do some type checking at compile time to figure out what's being passed, or what's the data type for a function. And how do we make that work? So we'll come back and we'll recap things in Lisp a little bit, and then we'll take a look at how some of this stuff works in C and C++. So on the Lisp side of things, again, the idea is the callee has a mechanism to take whatever was sent to it and test and see if it was actually a function. So there's that function P function that we played with that says, is this thing a function? And then if it is, we had a whole slew of different ways that we could take data that we'd created or data that we were passed and run the function on that. So things like eval and map and funcall and all the other weird and wonderful things we looked at. So it was easy to go through and make sure that at runtime we could check the data type that we were passed, make sure it's a function, apply it to some data, and then do whatever we want with the results. And of course, all of the type checking is then done at runtime, so we don't have to worry about any of this in advance. You can pass anything, and it's up to the callee to figure out if it actually got appropriate data. And of course, if anything goes wrong, then you've got runtime issues. But it's easy to deal with from the programming perspective, if you like. In C or C++, where you don't have that kind of a luxury, where functions aren't a data type in and of themselves, we have to come up with a different scheme. So the idea is the code for a function lives somewhere off in memory. Right? The actual object code, or pardon me, the actual executable code for whatever the function is doing is sitting somewhere in memory as the program's running. And memory addresses are just pointers, so presumably we could pass a pointer to where that code is as a way of sort of quote-unquote passing the function as a parameter. But that means that we need to have some kind of syntax for specifying a pointer to a function as a data type. And of course, that's where life gets a little bit interesting. So we'll take a quick look at that. If we take a look, I'm just going to sidestep here for a second, and we'll take a look at, what did I call this? Function addresses. So we've got this function here where at first all I'm going to do is say, well, let's take a look at how we can get the address of a function first off, and just see whereabouts it happens to live in memory. So all we're going to do in the beginning here is just use the name of the function, and in fact that's going to represent a pointer to where this thing lives in memory. So we're just going to print out the address of main and see where it is. We'll print out the address of f and see where it is, right? So we just pass main as or use the name main as the address of main, the name f as the address of function f, and we'll just see where it is. And then just to follow up on that, we'll take a look inside function f. We're going to stick a label in the code here. And then we'll print out the address of the label. This is kind of non-standard C++, but you can get away with it with our compiler. The double and will let you take the address of a label, so you can actually see where code is in memory. So we'll print that off just to confirm that, we'll get an idea for where f is, where the code for f is, and where main is. And then just for completeness, we'll print off the address of a couple of the parameter x and the local variable y, just to make sure that we're kind of on track here. Oops. Make sure we've got this up to date. And we'll run this. And you can see, okay, here's where main and f are, right? So main is at this address. Function f is really close by, a little earlier in memory. And then the code for f is just after the start of function f, which is kind of what we would expect, right? Function f starts here, and then there must be some housekeeping information there, right? There's 12 bytes in there. And then we've got the first instruction in function f must start right about here. And then we see just a little further along, we've got main starting, so it must have the code for f first and then the code for main. And then if we take a look, we see in a completely different area, we've got the code for the parameter and the local variable. So the runtime stack is existing over here someplace, and they've got separate space someplace for the executable code for the program itself, which makes sense, right? You don't want that stuff sitting on your runtime stack. So the other thing I wanted to take a look at is just the idea of creating a function pointer. So the way we do it is to create a function pointer, you set up essentially the profile for the function the kind of functions that you want to point at. So you have to specify what kind of a return type the function has to have and what kind of parameters it has to have. So in this case, I want my function pointer to be able to point at f. So my pointer has got to be able to point to a function that returns a long. The syntax for my pointer is put your asterisk, whatever the name for your variable is, and we'll just throw the brackets around it here. And then you give the types of its parameters. So this pointer can point at functions that take and return longs. And then we'll just see if we can make this thing point at function f. And then we'll see if we can call f through this. So now we should get the function running twice. Oops. How about we actually give it a data value to work on? So we should call f normally with value 3, and then we'll call it through this pointer with value 3. And let's hope I didn't mess up the syntax there anywhere. And so we get the first call here, where it goes through and prints off the start address and its parameter values, and then we get the second call here. So it is actually managing to call the beastie twice. I suppose, just for completeness, we should make sure that it's actually going through and getting the same values. So let's set, how about, let's print out the result of this. So the result is something weird. What did I do? That's a little bit more like it. So we've got the result printing off for the first one. Let's just do the same thing for the second one and make sure we get the same results. And then we can be reasonably confident that we've created this function pointer and that yeah, there we go. And we're actually working okay. All right, so that was all I wanted to show you just to get us kicked off there on the function pointer side of life. So if we can create pointers to functions and we can get the addresses of functions, then we can start creating higher order functions where we say, okay, I'm going to accept a pointer to a function as a parameter. So here's my higher order function. It's going to accept a pointer to any function that takes an int and a double and returns a char. And once it's got it, it's going to call that function, whatever it was, on 10 and 3.14, and it's going to grab the character that comes back as a result. So the data type for the function pointer has to be completely specified. So we're very limited in this, in that we can own this function, this higher order function, can only work on functions that take those types of parameters and return that type of value. So it is pretty limited, but it does work. And then again, you can call your higher order function passing it anything that actually has that profile. And of course, at compile time, the compiler can go through and look at this and say, does this sum function that you're sending off actually, it goes off and looks at the definition of the function and says, oh yeah, it does take an int and a double and return a char, so it's got the right type, so it all works out. So you can actually get your type checking this way, and things are reasonably consistent. But of course, that's pretty limiting from the point of view of what our higher order function can do. So if we could reduce this restriction, if we could get rid of this idea that we had to specify what data types, it would be a little bit more flexible, which of course brings us to templates in C++. What if we then took our higher order function and turned it into a templated function, where we took one of the data types for the parameters and said, let's just replace that with a variable for the type. So we've got our new higher order function that can accept a pointer to any function that takes two parameters. The second one has to be a double and it has to return a char, but this first parameter can be any data type at all. Or if we wanted to, we could take this further and say we could specify in our template, and this is what we'll take a look at in the lab example later. We'll give a list of 3 variable data types, right? 3 templated types, and replace, say, the return type with T1, type T1, replace the first parameter type with T2, replace the second one with T3, and then essentially your higher order function could take a pointer to any function that took 2 parameters and returned a result. And those 3 things could all be different data types and any data types. So really the only restriction is that the function you pass has to have 2 parameters. And this is where we can get to with our templated functions. Our function pointers are still limited in that we have to specify how many parameters the function is going to expect, but we're going to be able to make it accept any data types. So in Lab 10, that's exactly what you're going to be doing. You're going to be going through creating a templated, you're going to create a function that accepts templated function pointers as parameters and then calls them. And so in terms of the code, let's take a look at our templated function pointers. And here's where we're doing exactly the idea I was talking about, where we're going through and saying, well, I'm going to create a templated higher order function that takes a function pointer as a parameter. That function takes 2 parameters, possibly of different data types, type T2 and type T3, and returns a value, possibly of another type, T1. And then my higher order function is going to take a couple of other parameters and return a value. So in this case, what it's going to do is take a pointer to a function that takes 2 parameters. It's going to take a data value to send to the first parameter, and it's going to take a data value to send to the second parameter. And then it's going to return whatever the function returns. Right, so you pass me a function and a couple of data values to run it on, and I'll run the function on those data values and return what it returns. And this is just making sure that the 3 types actually match up. Right? Data type that F returns, we return. the data types of the two parameters, or the data types that funCall is expecting as its extra data values, and it's passing those to the function. So we could then go through, and I'm just going to explicitly instantiate, right? This is a templated function, so I want to go through and explicitly instantiate it, right? So I want the compiler to know that it's got to build a version of funCall for all ints, where T1, T2, and T3 are all ints. And that's what this instantiation is doing. It's saying, okay, let's instantiate funCall to return an int, take a function pointer that returns an int, takes two ints, and then we'll take our two integer values as a result. So the stuff in the angle brackets here is the list of the three data types to use for T1, T2, and T3. Right? So there's the T1, there's the T2, there's the T3. And then the rest of it is just actually declaring our version of funCall. Right? This is funCall is returning an int, taking this function pointer, and taking two other ints. So each time you instantiate funCall, you just give it in the angle brackets the three data types to use. Make sure you've got the return type for funCall at the front, you've got the function pointer as the first parameter, and you've got the other two data types as the other two. Right, so this one's taking two chars and returning a Boolean. And then this last one is just to throw three different types into the mix, so it's going to return a double and take a float and an int as the two parameters. So again, the three data types, T1, T2, T3, are double, float, and int. It's returning a double. There's our function pointer for the parameter, right? Returns a double, takes a float and an int. And there's the two data values to call f on, our float and our int. And then we'll just go through and create a few examples. We've got here one function product that uses our int version. So it returns an int, takes two ints, and it just returns the product of them. We've got something that just takes two chars and returns a bool if they're equal or not. So it just compares two chars and returns a bool. And then we've got one that's just an indirect call to power. So we're going to call power. It takes a float, raises it to the power I, and it's just using the math library pow function to do that. And then when we go through, we'll make three calls to those instantiated functions. We'll call it, we'll pass prod, we'll pass 3 and 5 as the values, and see what it does. We'll call same and pass it characters x and y and see what it does. We'll call power and pass it 3.5 and 2 and see what it does. But hopefully this does actually work. Cross your fingers. Whee! Okay, so multiplied 3 by 5 and said, yeah, okay, those are fine. It checked to see if x and y were the same. It said no. And we computed the square of 3.5, and we got 12.25, which hopefully is correct. So we can go through and create these higher order functions in C or C++ using these templated types. All right, I will let you play with that more in Lab 10.